Let's go ahead and get started. So a lot of you know me. Everyone should know me, I suppose. I'm Matthias, and I have the pleasure of hosting Javad Shabani today from NYU. So Javad is actually my first hosted speaker, which is very fun. And so quick story is that Javad was a postdoc in the lab I worked in as an undergrad at Harvard. My first real research experience, which ended up being kind of what I still do today in some form or fashion. So we kind of go way back, and actually Javad also is a PhD at Princeton, different lab. After his PhD, he went to Harvard for 2 years in that lab, and then UC Santa Barbara working on MBE and other materials.
Topological things.
Topological, working on Majorana fermions and all of that stuff. And then brief stint at City College, and now is at NYU, and is the director of the NYU Center for Quantum Information. So welcome, Javad, and excited to hear about what you're working on.
Oh, thank you so much. I hope you can hear me. It's a great pleasure to be here, and thank you so much for your invitation. And today I will tell you a little bit of the story of, as Matthias said, I was like an electrical engineering person kind of transitioning into physics, and now all of this is kind of connected through some quantum information science. So hopefully I can give you a broad view of why we are doing this, because I understand the audience is very diverse. And then I will kind of zoom in into some of the interesting and perhaps new directions that one can explore in quantum. I will not provide any solution that this is the way and you should do it, but more kind of like the variety of things that one can possibly try and why each of them might be a game changer. So maybe I can quickly introduce the Center for Quantum Information, because NYU didn't actually have much of a footprint in quantum over the years, but recently there is a lot of interest in City to actually help and engage in quantum information physics. And this new center now is trying to become a hub for industry, for gathering, for European interactions. And what we have been trying to do is to actually have multiple, I think we had 42 events last year, and some of them were having people talking about policies, and some of them were more science-oriented. And I think we had 12 high schoolers from 12 countries visiting us. And let's see. Yeah, and then the mission in just 1-2 slides is that it's like anybody else. You want to kind of have a scalable tech that hopefully makes a difference in our life. You want it to be open access. You want to bring some innovation to market through startups and things like that, if it's meaningful. But in my own kind of research, I really do semiconductor-based superconducting circuits, and I will talk about that more. And the other thing that I guess we should really hope to work as a community is to kind of try to democratize quantum, right? By that, it means share samples, share knowledge, work together, collaborate, and then things like that. We're also trying to basically build up on what Europe is doing. There is a lot of activity in quantum in Europe, and I don't think we need to reinvent the wheel at every university and every country, and how many quantum initiatives you can have, and then maybe there is an international of the quantum initiatives, right? So these discussions, I think, are very necessary and interesting, and the centers would definitely help to focus that kind of discussion. So kind of coming back to the talk, maybe I will kind of go back in many years. This plot is taken from a book called Singularity is Near. The y-axis is a figure of merit for computation power, and the x-axis is the number of years. And we kind of all agree that the computational power is increasing as we come to the modern time. But one thing that I guess is hidden in most of this kind of progress is that every time you kind of get an improvement is because you also change your technology, right? When we went from vacuum tube to transistors, that was a big jump. And then you try to optimize transistors until the next thing comes, right? And that next thing was integrated circuit. And again, when I was a teenager, I had Pentiums, and every few years it would be a better Pentium available. And I don't know, in the last 10, 20 years, I think that the GPU speed hasn't changed that much, right? It's 3.5 gigahertz. You want more, you just get quad and whatever. You buy just more parallel systems. And so that at least in this book, there is this like philosophical question that if there is something coming next, and I don't think if we're going to have a jump like that, right, we're not going to like let our laptop go and then have a quantum computer instead. But it could be that for specific applications, we need more powerful tools, right? And those could come in the flavors of quantum computing, maybe DNA computing, maybe all optical. There are lots of cool ideas out there. I will focus more on the quantum computing part because I think in terms of computing is a very foundationally different thing. And this is, again, not very new. People have been thinking about this for a long time. And one thing that I want to tell you is that, when we had this old technology, it wasn't like very obvious that this is not a good thing, right? It was actually, people are very smart, and when we were working on it, there were really good reasons why we should work on it. And for example, when vacuum tube was around, I actually took this from a literature from back then. It was like, there is no better device than vacuum tube. It is guaranteed because we all know electrons move slowly in solid. So why do you want to put this on silicon, for example? Like, this is the best device. And it's indeed is true. If you are sending something to outer space, probably vacuum tubes are still the best because there is no material that cosmic rays are going to interact with, right? So it's just vacuum, right? So it's all good. And people were brave enough, engineers, to make like these modules of, 8-bit and then kind of scale it up to this ENIAC that was the size of this room probably to compute something very simple. But then there were some visionaries like Feynman that were talking about like, quantum mechanics, things at nanoscale that would be basically very different, right? And you're all familiar with quantum physics and the scaling and things like that, right? So let me just do a very quick exercise to make sure we are all on the same page and you kind of get my philosophical direction here. So if I kind of draw a length scale problem, we know in classical mechanics we can solve Newton equations and everything kind of works. And I know that in quantum mechanics courses, atomic hydrogen is a perfect example. We know exactly how to solve it. It goes to helium, it gets a bit harder. Lithium, we just have to do approximations, right? But beyond all of this, if we just look from Feynman's point of view, when I was an undergrad or a grad student, almost every talk would start with Moore's law, right? It was like early 2000, and you're making things smaller and faster and more and all the good stuff. And in this very kind of simple graph, basically what it means is that we have some sort of a classical thing, like a transistor, and we try to make it as small as possible, right? And then if you ask, this is a CM image of a 40 nanometer, FinFET, but you could make now probably 10 nanometer, maybe even smaller transistors, right? But the rule hasn't changed. We are trying to still get a classical object as a transistor and make it smaller, but we know that at some point we transition to this quantum area, right? You will have like 20 atoms, now you have to really, solve Schrödinger equation probably. Now I can ask you the opposite problem. So what is the biggest object I can make that is fully governed by Schrödinger equation, right? So right, that's a reasonable question. I don't know if there is a law associated with that or a name, but atomic hydrogen works well. And we know at nanoscale everything is quantum, right? But then if I ask, what is this kind of macroscopic object? I actually asked this in another colloquium, and somebody said black hole. I really don't know enough to know that if black hole is completely governed by Schrödinger equation, but there are things that are easier than that. It really comes back to kind of our core understanding of quantum mechanics. In every system, I have some sort of an energy level, and it turns out actually the only criteria for making a macroscopic object is just these two. So I have to kind of have this energy spacing not smeared by temperature, so that puts like a threshold on my temperature. So I have to be cold enough for that energy levels. And then this is something that maybe we haven't been thinking about, is the dissipation, right? If the system is dissipative, I guess in optics you can think about this level broadening and things like that, or in disorder in some materials. If this gamma is also smaller than this energy spacing, you're pretty good. You can make as large of an object as you want, and it is only completely governed by Schrödinger equation. And examples of that exist. These are the two famous examples. This is a millimeter object that basically has an aluminum coplanar waveguide, and you can make a quantum mechanical harmonic oscillator, right? It's a 5 millimeter object. Why does it work? Because superconductivity basically allows you to kill dissipation, so this gamma is 0 in some sense, and the temperature obviously has to be smaller than this energy of the superconducting aluminum critical field, and then it allows you to give you delta E. I give you some numbers very quickly. And then the other concept is this topological system, like quantum Hall effect, for example, right? I can have a 5 millimeter object that, is just fully kind of quantum Hall, and in that sense also the temperature should be low, and the dissipation is taken care of by the topology of the system, right? Once I'm in a quantum Hall effect, I don't have dissipation, so basically I can have this. So I think, again, in my philosophical picture, basically all of these big objects come around sort of topology and superconductivity. And then if you can combine them to make a topological superconductor, that would be fantastic. In this talk, I would not talk about that. I would just talk about superconductivity. But I want to tell you that some of our success is really, it owes itself to the fact that we can make quantum mechanical systems much larger, and hence we have more control over them. For example, this is the example I showed you before, is a coplanar waveguide. What you need to do is just put it in a dilution fridge that is at 20 millikelvin. The TC of aluminum is 1 Kelvin. You can ask, what is this delta E? This delta E is basically practically the length of this is 10 gigahertz. That's about 500 millikelvin. So 20 millikelvin is smaller than 500 millikelvin, so I can really kind of look at the quantization. And the gamma is 0 because I'm superconducting, right? So if you want to get a length scale, right? If you want something at room temperature, now you need to work with something that doesn't have dissipation at room temperature, and the energies are really large, right? So if you think about atomic hydrogen, like the energy levels are like EV, right? EVs are like 10,000 kelvins. So room temperature is okay when you compare it to 10,000 Kelvin, right? But if you want something at the gigahertz frequency, this is the energy scale. And why do we want things at gigahertz? Because we have the best RF sources, right? We are really bad at making terahertz sources, right? But we also have really good lasers. So it's not, some of it's technological. It's not all like determined by our choice of what is my favorite system. So one more thing that is broad before I kind of get to the details of things is that somehow we are unlucky, I guess, or this is what the nature tells us, is that usually there is a tendency for quantum systems to become classical. And by that, I mean that you have an environment that would measure this quantum system, and basically you lose your superposition or whatever quantum effect that you had, right? So basically, it is kind of very unheard of that I just leave a quantum system and then I come back and it's highly more entangled, right? Usually what I find is that the environment that it lived around it, it basically measured it. And because of that, this word environment becomes important, right? And it goes into the architecture of the qubits. Like if I basically put ions in vacuum, it's very different. I put like a spin on silicon, or it's very different when I make superconducting qubit, right? Because each of the coupling to the environment is different, and that degrees of freedom basically brings this architecture that becomes important. So in our case, we're going to focus on superconductivity, on dielectrics, on how we can control things, how we can read things out, and for each of these, basically, there is an advantage. People working, when I was at Microsoft, we were working on topological qubits, and the promise over there was that, we are not sensitive to local errors or noise, we are only sort of macroscopic errors would just affect us because we didn't have this locality. So every qubit is different. So if you just consider solid-state solutions, there are, I think I counted once, it was like there are like 8 different type of qubits out there now. But the main solid-state ones are these topological ones, superconducting qubits and a spin. And these are the ones that we can have like 8-inch wafers and, okay, maybe 3-inch wafers at least to kind of start fabbing on, based on different physics. This controls the spin of an electron. This is, we'll talk about it. This is more like kind of electrical engineering, but in the quantum land. And this is very about the particles that we don't know if we have them in nature. If we have them, then we get Nobel Prize, and then we make a qubit, I guess. But then Microsoft is spending tens of millions of dollars on this. Most of the mainstream tech are investing in superconducting qubit because they are scaling up really well. Like, back then when Matthias and I met at Harvard, my project was to make 1 qubit, 2 qubits. But now, as you know, that people are making hundreds of qubits now, right? So things have changed. And so for those who are not familiar, or at least, they haven't, you want to see at least one good example that why we need quantum computers. This is kind of a cheated slide, but if you really ask very mundanely that if I have a classical computer with a 3 gigahertz of CPU and I want to kind of encode all the information I can encode in a number of qubits, how long will it take? You can see very easily that, let's say for 20 qubits, I have 2 to the power of 20 states. And if I really want to represent the whole space with that kind of clock speed, it would take me some hundreds of microseconds, right? But because adding each qubit will multiply the dimension by a factor of 2, once you get to about 50, 60 qubits, now you kind of are talking about hundreds of years, right? So that becomes impossibly hard for classical computers to kind of manage. But the problem is that I have a huge Hilbert space, as this is trying to describe. But the way I look in and I look out is your number of qubits. So I have a 2 to the power of 50 dimension in terms of my Hilbert space, but I can only measure 53 qubits. So that really kind of makes this comparison not very fair. But the fact that, when you add a qubit, the power goes by a factor of 2 actually adds quite descriptive, I guess, a picture of why quantum systems are very strong. So if you go out, as I said, there is semiconductors and superconductors. People are getting very serious about this. This is a report from Intel trying to make, I think this is a 7 qubit, but they have now a 12 qubit chip that you can actually contact them, and they will send you a chip with 12 qubits. You can measure it. This is a very CMOS process style that is basically run on a real fab line. And, semiconductors were always behind superconducting qubits, but now they are catching up. And the advantage of semiconductors of this type is that they are really small. Like if you look at them, these things are at the order of like 20 nanometer, right? If you remember when I showed you the superconducting circuits, they are at the millimeter regime, right? Because the wavelength is defined by this length, basically. So how do we choose what we want to work on, and how do we choose, do we want semiconductor or superconductor? And let me now kind of give you a material science kind of perspective before I try to make devices. So something that is very famous in superconducting circuits is that aluminum. Aluminum is the material that you want to go to if you want to work in this field. And what you can do is that you can basically evaporate aluminum, bring it in the air, it oxidizes, it's a self-limiting process, and then you put it back and you put another aluminum, you have a Josephson junction. I am pretty sure, I don't remember 100%, that when I was reading this Nobel lecture, it says you can actually try it with an aluminum foil in your kitchen. You can get it out, you can clean it up, let it oxidize, and then put another aluminum foil, you can make a junction. I'm going to try it with a very motivated undergrad in summer, see if it works. But basically, aluminum has that property that, that the oxide makes a very conformal layer. And if you look at these sort of very nice TM images, this is 2.4 angstrom. This is where aluminum was like your foil. You let it oxidize. This is this darker region. And then you try to put aluminum on top, and then now it's a little bit of a darker layers, right? But this was your bulk, so it looks very nice. But then there is a problem, right? Because if you look at this A and B and C, it looks pretty good by eye. I would say these are all the same. But when you look at this kind of atomistic intensity versus the distance, you see that the number changes a little bit. This distance where it sees the first aluminum to the first aluminum is 1.78, but here is 2.2, here is 1.5. So the difference is in tens of angstrom maybe, or maybe, I don't know, the worst case, let's say, is 5 angstrom. But in a tunnel junction, you are very exponentially limited to this distance, right? So this is quite a big, 5 out of 22 is almost like, right? This is a big number, it's a big percentage. So basically all of this current, if there is anything that is happening, is going to be in B, right? Basically A and C are kind of not really playing a game here, right? So this could be a problem. And again, if you go to IBM and say, how do you make 100 qubit? a good portion of the effort is focused on how to make these junctions uniform, right? And you make it small, and then you laser anneal it, and then do a lot of things to kind of really get this thing working. But the takeaway, I would say, lesson from this slide is that aluminum and aluminum oxide are like a magic given to us by nature, right? If we try this with niobium, it doesn't work. You can't even really get a junction, right? We are very picky that we say, oh, this is smaller than that, right? But if you can make it in the kitchen, then it's probably a pretty stable system, right? So in our lab, we try to continue on this magic. It's not easy. To do that, you have to force it. Now you need these machines called molecular beam epitaxy machines that are ultra high vacuum machines. The pressures are better than the outer space. And you basically try to bring each element separately, right? We do not try to do aluminum oxide. That's a self-limiting effect. We are trying to change the aluminum oxide with a semiconductor, with the concept that the semiconductors have new properties that I will talk about. So we can grow 2-inch and 3-inch silicon germanium, indium arsenide, InGaAs, gallium arsenide, some magnetic materials, and a good variety of superconductors. And I will talk about some of this as we go through, right? And it turns out, each material with different crystal duration has a completely different, is a different beast, right? The high melting temperatures don't want to grow thermally, obviously, right? You have to sputter them. Or if you want to deposit them, they are too hot. You have to actually deposit on a liquid helium stage. And things like that are very well known in material science community, but it's not guaranteed that you would get a good material. So I told you the aluminum oxide, and that kind of led to a Nobel Prize. If you go back to quantum Hall effect, where I'm coming from, if you read von Klitzing actually Nobel lecture, it's about, I think was paid to actually try to make a better FET device, a field effect transistor in Germany. And he ended up getting the best silicon on silicon dioxide interface. And because he had that interface, he could actually discover quantum Hall effect, right? So silicon oxide is a pretty good interface that happens, and that's why silicon worked so fast and better than germanium at the beginning, right? And then we become greedy, and then we put thresholds that then they cannot satisfy, right? Gallium arsenide, aluminum arsenide is another magical combination, right? People wanted to make lasers, they didn't know how to do it, then they realized, oh, gallium arsenide and aluminum arsenide have the exact same lattice parameter almost, and you can stack them on top of each other and alternate. Then they could do band engineering, and then once they could do band engineering, Alpasso and lots of other people at the labs, they kind of made these quantum cascade lasers, regular lasers, quantum dots, and all that. But then, Horst Dormer and Dan Sui and Art Gossard made this really clean 2-deck that could show electron-electron interaction and led to the observation of fractional quantum Hall effect, right? And those guys got the Nobel Prize in 1998. So I think we discovered these kind of combinations, but it was also given to us by nature, right? There were these accidental things that happen, and once you have access to those materials, you can really explore the in and out. And I want to kind of make a case for aluminum and indium arsenide that basically creates a very specific interface. Now I am trying to put a metal on top of a semiconductor, and germanium seems very, very interesting with different combinations that I may just like flash 1 or 2 slides today. So this is the aluminum on gallium antimonide. Indium arsenide and gallium antimonide have almost the same band structure and crystal. So basically now you can see that with the proper way that we are growing this with MBE, we can get, this is 2 nanometer scale bar. You can kind of like see exactly how I transition to a superconductor. And if you look at the lattice of aluminum, it's much smaller than indium arsenide or gallium antimonide. But then magically 5 atoms of aluminum basically match exactly with 2 unit cell of indium arsenide and creates a perfect interface as if like they were like a perfect match, right? So this is something that we are trying to build on. And from the physics point of view or the engineering point of view, when I have this device that basically has aluminum and some indium arsenide or a semiconductor in the middle, I can say, in aluminum oxide, it was just a tunneling, right? But now I have a transistor that the source and drain are superconducting, and on top of that, I can put a gate that controls the number of electrons in my semiconductor. So I can get supercurrent out of this device, but by changing the gate voltage, I can deplete my electrons that the supercurrent basically drops and almost vanishes. So I can create a gate-tunable supercurrent in some sense, right? So this is my Josephson field effect transistor. I can make transistor switching very fast. I can do fast things here. And the power consumption is almost zero, right? Because there is voltage applied, but the current that goes through this gate is zero. So voltage times I is zero. So basically, I'm not really like using any energy. It's just all like logic. So we will talk about it, but basically, once you have such a thing, now basically you can change the inductance of this junction through the gate voltage. And if you can change the inductance, imagine the resonators I showed you for harmonic oscillator, the frequency is 1 over LC. So now I can change L, I can change the frequency of the qubit or whatever you want basically, right? Or if it's an amplifier or if it's a resonator, anything that is, I can basically just by applying a gate voltage switch it, right? And the other thing is that because now we have these semiconductors that we are adding the superconductor to it, is that I can go back to kind of like CMOS and then propose this question that, okay, I have my qubit system out there. Can I make my control motherboard cold, right? Because if it's all semiconductors, can I do the standard whatever processor that we do for motherboard and kind of put it next to my qubit circuit and then see if they can control each other and just give me the final answer rather than basically setting the IOs. But these are a bit futuristic questions, I guess. If it's working, we will pay anything to get it, right? We don't have to do this. Having this kind of switch, basically the Josephson field effect transistor is like a good switch. I can actually propose things for quantum memory. Basically, if I have a really, really good resonator, it could serve as my memory element, let's say down here. But the problem is that when I kind of make a circuit, imagine I have a mirror that a photon is in this side in the resonator, right? If it's a really good mirror, that means that I will never ever see that photon outside, right? But when I want to do a computation, I actually need the photon. So I can't just wait like for seconds for this atom to come. So if I have a switch that basically takes the mirror away and the photon comes out, now I can read out by a readout signal. So basically I say, I send an RF, I send a DC line. The moment that I turn this on, the photon comes out because now basically it shorts the resonator out. I can get a swap operation with my bus line, then I will basically cut it down, right? So if you have a switch in the superconducting circuits, actually it can take you a long way. And this kind of devices are sort of the beginning of this, and then with IBM we proposed maybe a QRAM that can have 64 memory element, right? Because everybody's making a processor, you can say, why not peripherals, right? So this is in that concept. And the list goes on. Like I will talk about Gatemons a little bit today. There are topological versions. There is microwave to optic transduction. You can say the semiconductor has a band gap, unlike aluminum oxide, which has a very high band gap. And because these things are infrared, maybe we can actually do better transduction. We have shown we can make amplifiers. We have proposals on the memory. We have a proposal on quantum router. Because if you have a switch, now basically you can do impedance mismatching in a superconducting circuit. That's usually hard because you have usually 2-terminal devices. Now you have a 3-terminal device all of a sudden. So going back, where is the state of the art, right? I'm just telling you this JFET is the best thing. So what people have been doing in superconducting circuit has been using these SQUID loops. So because if you have a SQUID loop and you have a flux line, by passing current through this line, you can actually induce a magnetic field inside the SQUID, and that would exactly almost do what you are doing with this supercurrent, right? You can kill the current, you can increase the current, you can tune the current, and that's what Google actually is using for couplers and for the tunable frequency qubits. They call it XMON. IBM uses fixed frequency. There is nothing that is tuned, right? The difference is that, okay, first you are sensitive to flux noise. Over here with my new device that I introduced, I have charge noise. I can do it fast and the power is very low because as I said, the power is almost zero. Here you are dissipating current through this wire. So if we ever get to 1 million qubit, you have to think about how can you basically, if you have a superconducting wire at some point it's probably not superconducting because it has to go from the top of the fridge. And you can ask how many milliamps you need times how many milliohm. Is going to be a huge amount of power that will be dissipated on the fridge. So in terms of power, this definitely wins. In terms of control, this can work. Really the question is what type of things you want and how you want to scale up. So semiconductors are nice because then you can go buy the largest wafer you want. You can probably put the stack together. This would be my ultimate stack if I really want to zoom in and tell you exactly how I make this aluminum on indium arsenide. In our lab, we actually use 2-inch wafers. The reason is that the 2-inch wafer cleanliness is much more than the 8-inch for 3-5 materials, for indium phosphide. For silicon, they have made the state-of-the-art to almost, it doesn't matter, 2-inch and 8-inch. But for 3.5s, actually 2-inch is the best quality. You cannot, by going to 3-inch, you're actually losing the quality. The stack is quite complicated because the lattice parameter of indium phosphide is very different than indium arsenide. You have to do this metamorphic growth, and then you do silicon doping. And once basically this comes at the surface, it becomes electrons on the surface, like graphene almost, and then you put the superconductor on top. Indium arsenide by itself is known that basically it has a negative Schottky barrier. Like if you just get like a regular silicon and you put aluminum on it, it moves the electron away from the surface because it pins in the mid gap, right? So if you draw this band diagram, basically you have a slope and then the electrons push in. But in indium arsenide, it does the opposite. It basically brings the electrons to the surface when you put metal. So because of that, we can put it on indium arsenide, but we basically lower the Schottky barrier to 0.81. So basically, we just don't have a rush of electron at the surface. We just get the right number of electrons that we want. Then we can put this epitaxial aluminum on top of the InGas. So this is kind of the structure that we will use throughout the talk. And we can grow we grow one a day now, and for various collaborators and various projects. So I want to show you this as kind of the variety of what you can do. So basically what I talked about was this aluminum, indium arsenide aluminum. And to create a gate, now it's again electrical engineering task. What is my gate stack? Should I use high K dielectric? What should I use a regular? And that's a challenge in our field because, yeah, sure, we can use aluminum oxide, but it has so many defects that once you drive it in microwave, it absorbs like crazy, right? So if I want it for qubit, that's actually not a good option, right? But if I want to do DC, it's probably okay, right? I can just DC bias it and then look at the properties. So we do both, but then in the middle, we realize that, we learn from 2D communities, like there are these talks about graphene and HPN, and I had a postdoc who said, let's just put HPN as a dielectric. So we got like this transfer setup, and then she puts this graphite with HPN instead of this aluminum oxide, and graphite is basically your gate. And you can look at the kind of the gate voltage dependence of resistance as a function of bias. So this dark region is where you sort of see this zero resistance state or the supercurrent. And you can see that you can tune this supercurrent quite nicely from 0 to some finite value. It's almost the same thing as aluminum oxide, right? So now this one can go to microwave, and HPN is a single crystal, so it doesn't actually have much absorption as aluminum oxide has, right? So this story with material just keeps moving around, right? Because your criteria keeps changing, right? If you want like a standard transistors, maybe it doesn't matter, but if you want now to do qubit, every single photon matters. So now you can do what you were doing in classical transistors, for example. So a graph of this is very typical. As I showed you, this gate voltage as a function of bias current, and this is the amount of supercurrent. So if I want to sort of see how much it is, I basically draw a line. It would be a few microamp. If I plot that on this graph, it would be basically switching current as a function of gate voltage. And as you see, I can basically measure the amount of current that actually goes from some finite value to 0, right? But then you can actually convert that current into the inductance. So there is a formula that basically translates how much supercurrent you have to the inductance. For example, for transmons, you want about 10 nanoamp of supercurrent. Like here is microamp. This is too much, right? You don't get the right frequency for the inductance you have. And basically now, if you look at this red graph, you see that you have a few nanohenry here, and then it basically takes you to a really small number. So if you want to make a transmon, now you basically gate yourself down until the current is correct, and then you can sort of like run a qubit. So basically the supercurrent scales as the square root of voltage. So I will give you 2 examples of a tunable resonator and a Gatemon, and then I will try to discuss a bit about material and wrap it up with some future directions. So if I want to make a tunable resonator, you all know about resonators hopefully by now. it's just a strip of aluminum on top of a dielectric. By tunable, I mean, so I have this in and out. This is kind of my bus line. This is your resonator in the simplest shape. We call it L shape. And then you put a junction before it shorts to ground, right? So now you can think of two obvious cases. Like if the junction is open, so I have now basically open to open resonator. And if it's short, basically I'm shorting to ground. So I can go from lambda over 2 to lambda over 4. That's as the minimum. But then I can also think of a circuit that I have an inductance here that I can change. So I will talk about that very quickly. And I can basically bring the whole like qubit circuit out. So basically this is my readout. I couple to a resonator for dispersive shift. This is my qubit with a T-shaped capacitive island. And now the extra thing that I have is this gate voltage. So I will briefly also talk about that and then why we should maybe care about this Gatemon type things. So first, the tunable resonator, I basically have this 50 ohm line that comes in. I have the junction to ground. Imagine the junction is gate tunable, right? So this is the gate tunability. And what I would find for, perfect, this tight. What I would try to get the frequency for, it would be related to this L0, the fixed part of the resonator, and this Lj, the junction inductance, right? Capacitance is pretty much fixed. The Lj, as I said, is inversely proportional to the supercurrent. Supercurrent is a function of gate voltage, so I should be able, if I measure the resonant frequency of this with a VNA, and I sweep the gate voltage, I would expect that resonance to change, right? So this is the circuit, and let me see if I can show you the data. I'm going to skip this. This is about kinetic inductance and a bit more complicated for this talk, I guess. But then here is, you see that as I sort of sweep the gate voltage, I had a resonance around 6 gigahertz that now is changing and moving down to 5.5 gigahertz. So in some sense, I have 500 megahertz of tunability. That's good. It's not great. It actually goes more. But here what I can do is that I can ask the reverse question. I can say, if I have this data, how big is my Lj? Right? I would like to kind of characterize my junction because I know, again, I guess you looked at the figure. The junctions are pretty wide. I can make them narrow. I can make them very wide. So then there's a self-capacitance associated with it. So we can characterize all of those, and basically from the Lj, we can deduce the current back, and the current we get about 1.5 microamp. You can do a DC measurement and you almost get the exact number. So basically from the elemental analysis, it actually makes sense. Right? If you just assume the junction is an inductor, you measure it independently, or in the circuit, you will measure the same thing. So we said, okay, this is very kind of boring in some sense. It worked and it was supposed to work. What if we put another resonator here and put it on the way of this guy? Right? So basically, with one resonator that is tunable, I can change the frequency, but I will put the other guy in the middle of that frequency, so it has to go through it. So once they have a crossing, the information will be sweeping back and forth. Basically, it's a swap operation, right? So this is kind of the fixed resonator. This is the tunable resonator. And now you see that the tunable resonator, I can tune it from 6 gigahertz to almost maybe 4 gigahertz. And the fixed one is at 5.3, 5.35. And it shouldn't change with gate voltage as it doesn't. But then when the two resonators see each other, there is an anti-crossing because they're coupled through the bus line. And you can basically find out what is this crossing, and I will show you in a second. But at this point, basically, I have a photon that jumps from one resonator to the other one, and then from the other one to that. So if I time it right, I can basically get a swap operation in some sense. So that's where these tunable resonators come very handy as couplers in some sense, right? If you have two qubits, you put one of these in the middle, you can basically sweep to where you want it to be and then move away when you don't need it. Okay, cool. So this is kind of a zoomed in on that anti-crossing. You can try to fit it and then see how fast can I swap between the two resonators. And what we get for this G is about 50 megahertz. That's pretty fast for a circuit. Like you can get within tens of nanoseconds, you can actually swap two information from two different circuits. And we can do HFSS calculation to actually show that basically electric field is distributed equally or actually just hops back and forth when you are at that critical point, right? So this is finite element calculation. So again, in terms of an element, this is turning out to be a really good tunable system. It doesn't cost us much to operate it in terms of power. And now what we are trying to do in this experiment, we only had DC cable going to the fridge. So we couldn't, ideally what you want to do is to basically come to this point for 10 nanoseconds and then go back. And then at that point, you basically swap exactly 1 photon, right? But because this was DC, we had to sweep through, and basically it's a very steady state type thing. So now in the new experiments, we are actually putting VG on a biopsy that can actually apply microwave at the same time. So, but the general purpose of that is working. So when we were making these JFETs, we were talking to, the real people who do superconducting qubit for life. And their question was, oh, this must be lossy. Like, this can't be a proper junction, right? Something must be wrong because it's semiconductors or something. And by talking to various people, following Irfan's work early on, this also, okay, yeah, somewhere there. It turns out if you have an oscillator, which is a harmonic oscillator, a resonator, right? If you drive it with high power, it becomes a very specific object. It becomes a very nonlinear object. And this nonlinear object has a universal, basically, relationship between the power that you put in and the frequency that you measure. And if it is following that rule, it basically means that there is no other funny business going on with the dissipation of that junction. So we have this paper with Vladimir Manucherian and other people, Maxime, that basically we drive one of these resonators I showed you with extreme power, and we look at this kind of omega parameter that is relating quality factor to frequency, and these are the universal curves that you're supposed to get, and we get the same thing for all the gate voltages. Because one thing that I didn't really dive into is that, aluminum oxide is a tunnel junction. Here I have semiconductors, meaning that I have Andreev bound states. Okay, perfect. If I have 100 good Andreev bound states, I'm in a good shape. But when I go to minus 8 volt, maybe my Andreev bound states are lossy. Maybe they are resistive. Maybe there's a problem, right? So it's very especially important to kind of know that when you kind of are depleting these junctions, do I have kind of resistive modes out there? And the answer is that pretty much we don't see anything over 2 decades of data. So as an element of the circuit, again, it works perfectly fine and is nice. So something that I just want to flash, because it's kind of part of this sensing and the resonator, is that if you have a resonator, basically you have a frequency, right? And this frequency could change based on how the resonator elements are changing, right? But what you can make this resonator into a quantum sensor is that by adding basically a SQUID loop at the bottom of this resonator. So now instead of having a resonator that goes through a gate to ground, I can make a resonator that becomes a SQUID, but it has 2 gates. So previously I just had 1 path, but now I make it 2 paths. And by putting a pi phase shift over here, you make this element a quantum sensor practically, right? So, and we can show that this sort of a SQUID can detect if 1 Cooper pair is broken, it gives you enough frequency shift that you can actually pick it up in the sensitive device. So this is kind of the chip that we have. This is the bus line, and then there are the resonators that basically have a SQUIDs that are all fully gated, and we can control the asymmetry and the symmetry of the gate. We can basically put a phase over here. And in this particular experiment, which was a quasiparticle poisoning experiment, the device was so shielded that we couldn't get any non-equilibrium effect. So we had to put these injectors on the side to actually inject photons. And then we kind of see a decay of time scale of the decay of these quasi-particle events. But what was really cool that we didn't think about it is that how do we create a photon that actually talks to this SQUID loop? And the idea was at the end, with Maxime helps on the theory side, was that probably these photons gets coupled to phonon in the indium phosphide, travels all the way to the SQUID, and then it converts back. So basically, this time scales, I guess I'm not showing the time, is like a few microseconds, is actually the conversion factor of electron to phonon coupling of this device, and we are actually trying to estimate this better, that like, for example, aluminum to indium arsenide, what kind of times do we get for the electron-phonon coupling. But For the sake of time, let me just try to tell you quickly what other elements I can make, and then I have basically a Lego game. I can make a tunable coupler, I can make a memory, I can make a qubit, and can I put this together? How bad it is, how good it is. So the fab starts very funny, right? I have a wafer that has epitaxial aluminum on it. I just have to remove things I don't want. So you basically remove this island. This T shape is just a capacitor. This is the drive line. This is the readout. And basically you come and then define a junction down here for the people who do nanofab. And then basically this finger aluminum gate is going to be the gate that controls the supercurrent. So this is a SEM image. This, I think I already showed you. This is the bus line, and I will tell you the physics of how you measure this in a second. This is a bigger version, sort of zooming up here. You see there is a junction there. I mean, it's super hard to see, but the gate is going right over that thing. So the way that we measure it is that we look at the frequency and the VNA over here, and then we drive with a signal generator on the side. This is very standard transmon circuit. So what it is that basically this resonator acts as like these two mirrors in the cavity SQUID literature. That basically has a Hamiltonian, right? That Hamiltonian is this Hamiltonian that basically has A dagger A. You put your artificial atom or qubit basically right in the middle of it. That has its own Hamiltonian that basically is a Bloch sphere with a Z up. And then there is an interaction term that basically really makes this guy talk to this guy, right? So that would be your interaction. In this case is basically capacitive coupling, right? So if you have this resonator, it's a very famous Hamiltonian. You can solve it in many limits. But the way that it works best, if the resonator is kind of weakly coupled to the qubit, then you can kind of do this approximations and actually calculate exactly what you expect for readout and everything else. So we do that to actually read out the information of the qubit. So basically, let me go back. Whether the qubit is in this state or is this state will basically have an impact of the frequency of this resonator. And this is how we can do a non-demolition measurement on the state of the qubit, basically. So in our qubit, things are a little bit different. The way that we tune up our qubit is that we basically sweep the gate voltage as a function of frequency, because we have that capability, right? So we know that we can tune our frequency of the qubit. And the moment the qubit goes into a crossing with a resonator, we get an anti-crossing. So this is a resonator, this is the qubit. So then we know which one is qubit, which one is resonator. Then we don't confuse ourselves. Once we know the qubit, then we can sort of tune the qubit frequency again over a few gigahertz. The problem that you see is this wiggly line. If it was a gate voltage and a supercurrent, it should be a perfect line. Right? Because I'm decreasing my carriers, my frequency should go monotonically. But what happens is that this dielectric stack that I mentioned earlier, and this one is not HBN, is actually aluminum oxide, basically has this hysteresis behavior. So you're trying to go down, and then it charges up, it stops, and then it goes down again, which is quite annoying in this. But you can nonetheless try to do a Rabi measurement. So basically, you are looking at your readout, see what comes out of the qubit. And for a very short time, you basically drive your qubit, and then you look at this coherent oscillation. In our first generation devices, the T2s were around 20 nanosecond, and T1s were 45. So T1 is the one that basically takes your qubit from up to down. But basically, you put it on up, and then say, am I up, am I up, right? And then at some point, you see that you're completely mixed, right? So these numbers are, maybe they were great a decade ago, but now it's nowhere near a state of the art, right? At IBM, you can get numbers that are tens or hundreds of microseconds now, right? So it's kind of orders of magnitude lower. But now what we have is this kind of capability at the research level to change things and also tune things with gate voltage. And if we think that this is the way, then we have to optimize and go forward, right? So for example, we should go from oxide to HBN, the T island versus paddles. Should we really just put DC into the qubit? Maybe we need to do filtering. Maybe we actually do it through the RF, aluminum thickness. When we did this experiment, our aluminum was 210, and we didn't think that the electric field between two aluminum planes, if it's very thin, is going to go toward the substrate. So participation loss from the substrate is going to be high. But if you grow your aluminum very thick, now the participation that goes into the substrate is going to be less, so that basically the absorption is going to be less. Anyway, but now we can routinely make 4 to 10 qubit devices. We can basically pick all the resonators. We can get the crossing at the level of 100 megahertz with a qubit. And sometimes we are not IBM, sometimes it doesn't work, but then many times it works. So we can now consistently go to a few qubit regime. We can do readouts the same way that everybody does. Basically, you look at the resonator based on when the qubit is on or off, and then you see that basically this dispersive shift would help you to kind of identify what is the state of the qubit, right? So all of this together, now we are improving our times within our ward. You get the Rabi oscillations. We are now about 50 to 100 nanosecond, I would say, in the latest. And the promise is that, okay, where are we going? Like our qubits very, very bad compared to the state-of-the-art qubits, but as a coupler, we are pretty good, right? So basically imagine I have, I don't know, the best 100 microsecond and 100 microsecond qubits, but I make a gate voltage tunable coupler in between. You can actually show theoretically that if this coupler really bad at this level of coherence time, it actually doesn't add much to or harm the fidelity of a 2-qubit gate. It's just like basically a bypass agent that error doesn't come in. So that I think would be very, very interesting. The other thing is, if I can measure I can change this by gate voltage, that means that basically my frequency, I can change it. I can change my T1. And if things were proper here, I can say, oh, look at this part. The frequency is not changing much here. I have a sweet spot, right? Basically, the first derivative is 0. So here, my T1 should be highest. Oh, it is highest, but it's not as high as I want it to be, right? So I think there are also these sweet spot games that you can play with gate voltages and find yourself in pushing your times up as much as you can. But the real promise is to actually do fast gates, not DC gates. And also, you can also go from dispersive readout to longitudinal readout in these cases. That would help you to actually overcouple to your qubit. And then basically the qubit state doesn't go bad. So we have done a lot of statistic and measurement. Again, this is like a 200 nanosecond time scale. But a lot of this is material science again, right? The fact that how can we push 200 nanosecond up? You have a piezoelectric substrate. You are using aluminum oxide. You basically have to kind of go on the drawing board and then write the best things that you can. One question that we had ourselves, which was really good exercise, and I'm going to wrap up with this last few slides, is that we said, okay, indium phosphide, bare material. What is the quality factor of indium phosphide? The one that we can measure in our lab is, I don't know, 20, 30,000. So, okay, great. Let's make it on a new substrate, on an indium arsenide substrate. So we measured it, and it was a factor of 10 lower. We said, okay, what's the problem? Maybe the MBE material that we're putting on is bad. But then my student looked at this, and I said, let's make a full device. And then maybe this is something. So we made a full device. It was an order of magnitude worse. Because when we put the gate on top, it basically trashed everything. And after the fact, we looked at this and said, like, this actually makes sense. Because I have microwave, and this is gold, so it's dissipating. So basically now I'm dissipating everything out. Let's change that gold to aluminum. We check to aluminum, we get our baseline. That's great. Then it's like, so why is this guy different than that one? Is it just because I'm growing material? And the student said, this is 30 nanometer, that's 100 nanometer. Maybe that's the difference, because of the participation that you get from 30 nanometer is different than 100, and indeed it went back up to basically the baseline of indium phosphide. So one of our biggest challenges now is to moving away from indium phosphide. We also changed, our kind of RF hygiene to fully professionally made microwave kind of circuits that, again, the quasiparticle measurements between the two are not even comparable. We can now look at niobium on silicon with quality factors that are 1.5 million in this new setup. So we are pretty comfortable that the setup is nice. But the indium phosphide is the biggest problem, because with indium phosphide, we cannot really beat 50,000 quality factor, right? So what do? I have a system that indium arsenide and aluminum was the magic part, but whatever I grow it on is bad. And what you can do is, let me skip this because that's interesting. I guess what I can do, I can give you the answer, is that to basically go from indium phosphide to silicon. How do you do that? You grow T5 on silicon. And this has been done. Actually, if you go to optoelectronic people, they have been making lasers on T5, but T5 is very expensive. So they actually have a process that they transfer it to silicon to be cheap. So we are actually working with some optoelectronic company now to transfer this stack onto silicon. Let me give you 2 more material examples, and that's it, I promise. So you can go away from aluminum. We have tried niobium tie, and we can get cross-sectional TEM images that look very nice. Niobium tie is very resistant to magnetic field, right? The critical fields are like 15 Tesla or so, and the TC is 9 Kelvin. So that's the new playground that we are working with. Another really, really interesting system is tantalum on germanium. We have been growing this, what I call tantalum germanide on germanium with MBE. And what we can see is that, I don't have the TC here. TC is about 2 Kelvin. This is the critical field of in plane is 5 Tesla, and out of the plane is 2 Tesla. So now we can get almost epitaxial, this tantalum germanized on germanium. It's really not tantalum, it's tantalum germanized, that we can use as a new super semi. And germanium doesn't have the piezoelectric problem. So maybe from aluminum indium arsenide, we want to completely move to germanium. So that's kind of the new direction that we are pursuing. See if that's possible. Germanium is the best next thing. Like you want to be group 4, right? So this I already talked about, this optoelectronic companies that they do professionally gallium phosphide on silicon. And let me skip this for the sake of time so we can at least have some questions. These are the new HBN qubits. Anyway, thank you.